Welcome to Le Podcast de Philippe. And today we're doing a deep dive into something pretty cool. Aerospike engines. You know those classic rocket engines with the big bell-shaped nozzles? Well,
Mhm.
these are totally different.
Yeah, they're way more efficient, especially at low altitudes, and they can really change the game for space travel.
Exactly. And get this. A company just designed and test-fired a working Aerospike engine that was completely created by an AI. And the AI did it in how long?
21 days. Can you believe that?
It's mind-blowing, right? So today we're going to break down what makes these engines so special. We'll talk about how they work, the different types, and what this AI breakthrough really means for the future of space travel.
It really is fascinating stuff.
Definitely. So let's start with the basics. What exactly is an Aerospike engine, and what sets it apart from the traditional rocket engines we're used to seeing?
Well, you know how those traditional engines have that big bell-shaped nozzle to direct the exhaust?
Yeah, that's kind of their signature look.
Right. Well, an Aerospike engine throws that out the window. Instead of a bell, it has this central spike or ramp.
Okay, I'm picturing that. So how does that actually work? What happens to the exhaust?
So the hot exhaust gases flow around that central spike, and as they do, they interact with the surrounding air pressure. And this is where it gets really cool. That interaction creates what's called a virtual nozzle.
A virtual nozzle. That sounds kind of futuristic.
It is. It's basically an invisible nozzle shaped by the exhaust and the air around it.
Okay. But how does that make it more efficient than a regular bell nozzle? I mean, why is a virtual nozzle better?
It all comes down to adapting to changing altitudes. You know how air pressure gets lower as you go higher, right?
Yeah, like when your ears pop on a plane.
Exactly. So a traditional bell nozzle is designed for a specific altitude, but as the rocket climbs and the air pressure drops, that bell shape becomes less and less effective.
You can't keep up, right?
Exactly. But the Aerospike engine, with its virtual nozzle, well, it just adjusts. That virtual nozzle expands and contracts, constantly fine-tuning itself to the changing air pressure.
So it's always working at peak efficiency, no matter how high the rocket goes. That's impressive. And I guess that's one of the reasons why this AI design engine is such a big deal.
It is. I mean, designing a rocket engine is a huge task. It usually involves big teams of engineers, years of work, you name it.
It's rocket science, literally.
Literally. But this AI, Noyron, created a fully functional design in just 3 weeks.
21 days. I still can't get over that. But did they actually test it? Did this AI designed engine really work?
Oh yeah, they fired it up. The test happened at Airborne Engineering in England, and the engine performed amazingly. It generated 5,000 newtons of thrust, which is pretty powerful.
So it had the muscle.
It did, but more importantly, it survived the heat. We're talking exhaust temperatures of 3,500 degrees Celsius.
That's hotter than, well, a lot of things.
Yeah. It is. Most metals would melt at that temperature, but this engine held up. It was made from a special copper alloy using 3D printing, and it passed the test with flying colors.
That's incredible. Talk about a hot debut.
I'll say. It really shows the power of AI and advanced manufacturing in aerospace engineering.
It's a game changer. I
Yeah.
mean, this isn't just a cool science experiment. This technology has the potential to reshape the future of space travel.
Oh, absolutely. Think about the challenges of getting a rocket off the ground and into orbit. It takes an enormous amount of fuel, right? Especially in those first few minutes when the rocket is fighting against the thickest part of the atmosphere.
Right, every pound of fuel matters.
Exactly. And that's where Aerospike engines really shine. Their efficiency at low altitudes means they can significantly reduce the amount of fuel needed for liftoff.
So a lighter rocket, less fuel, what does that translate to in practical terms?
It opens up a world of possibilities. We could launch bigger payloads, build smaller and more cost-effective rockets, and even start thinking about more ambitious missions.
Like what kind of mission?
Well, think about exploring the outer solar system, or even establishing a permanent base on Mars. These are missions that would require massive amounts of fuel and resources. But with Aerospike engines, those missions start to become a lot more feasible.
So we're not just talking about incremental improvements here. We're talking about a fundamental shift in what's possible in space.
Exactly. Aerospike engines have the potential to be as revolutionary as the jet engine was for air travel.
That's a pretty bold statement. But I can see why you're so excited about this technology. It really does feel like we're on the cusp of something big.
We are, and this AI-designed engine is just the beginning. Who knows what we'll be able to achieve in the next decade or two?
It's an exciting time to be following the developments in aerospace, for sure. But before we get too carried away, let's take a closer look at the different types of Aerospike engines that are being developed. I know you mentioned there are a couple of main configurations, right?
There are. The two most common are the toroidal aerospike, which is circular, and the linear aerospike, which is, well, linear.
Like a donut versus a breadstick.
Yeah, kind of. Both types operate on the same principle of using the ambient air to create that virtual nozzle, but each design has its own pros and cons. Engineers are still exploring the best ways to utilize each configuration for different missions and applications.
So there's still a lot of research and development happening in this field. It sounds like Aerospike technology is still in its early stages, despite the concept being around for a while.
It is, but things are moving fast. The advancements we've seen in recent years, especially with AI and 3D printing, have really accelerated progress, and I think we're just scratching the surface of what's possible.
I'm definitely eager to see where this technology goes in the coming years. But before we get ahead of ourselves, let's talk a little bit about the challenges. I mean, designing and building these engines can't be easy, right?
Oh, definitely not. One of the biggest hurdles is heat management. Remember, we're talking about exhaust temperatures that can melt metal. So designing an engine that can handle that heat over long periods is a major challenge.
Makes sense. And what about the design itself? Creating an engine that essentially changes its shape on the fly must require some pretty advanced engineering.
Absolutely. The complex geometry of the Aerospike, the materials needed to handle those extreme conditions, the precision required in manufacturing, it's all incredibly demanding.
So it's not just about coming up with a cool concept. It's about turning that concept into a reliable and functional engine that can actually perform in the real world.
Exactly. And that's why there's so much research and testing going on. Engineers are constantly pushing the boundaries, trying new materials, refining designs, and running simulations to ensure that these engines are safe and efficient.
Well, it certainly sounds like a challenging but incredibly rewarding field to be working in. I mean, to be at the forefront of developing technology that can literally take us to other planets, that's pretty amazing.
It is. And it's not just about space travel. Aerospike engines could also have applications here on Earth, like in hypersonic flight.
Okay, now that's something I definitely want to hear more about, but I think we'll save that conversation for our next segment. For now, let's keep focusing on the space exploration side of things.
Sounds good to me.
So we've talked about the basics of Aerospike engines, the different types, and some of the challenges involved in developing them. But we haven't really dived deep into the why yet. Why are these engines so crucial to the future of space travel? What kind of impact could they have on our exploration of the cosmos? And what about this AI-designed engine? What does that breakthrough tell us about the future of aerospace engineering itself? Those are some of the questions we'll be tackling in the next part of our deep dive, so stay tuned because things are about to get really interesting.
I can't wait.
Me neither. And for our listeners, if you're enjoying this deep dive into Aerospike engines, be sure to subscribe to Le Podcast de Philippe on YouTube and hit that notification bell so you don't miss the next part. We'll be back soon with even more insights and discussions about this game-changing technology. Until then, keep looking up. All right, so we're back and ready to dig a little deeper into the potential of Aerospike engines. Before the break, we were talking about how this AI designed a working engine in just 21 days. That's pretty wild, right?
It really is. It kind of blows my mind, how fast AI is advancing.
Me too. And what's even more exciting is that this is just the tip of the iceberg.
Exactly. This AI, Noyron, it showed us what's possible. It's like opening a door to a whole new way of designing and engineering.
So we're not just talking about faster design times here. AI could actually help us create entirely new types of engines, ones that we might not even be able to imagine right now.
That's the really exciting part. AI can analyze huge amounts of data, explore all these different design possibilities, and come up with solutions that would take human engineers years, maybe even decades, to figure out.
So it's like having an AI partner, pushing the boundaries of what's possible. But are there any downsides to incorporating AI so heavily into aerospace engineering? I mean, it sounds almost too good to be true.
Well, there are always challenges with any new technology, right? And
Right.
AI is no exception. One of the big concerns is what's called the black box problem.
Black box, like a mystery box. What's that?
It's this idea that with these really complex AI systems, it can be hard to understand how they work, like
Yeah.
how did they get from point A to point B? What logic did they use?
So it's like the AI is making decisions, but we don't necessarily know why or how it's making those decisions.
Exactly. And that can be a problem, especially in aerospace, where safety and reliability are so critical.
Right. I mean, if we're going to trust AI to design engines that are going to carry humans into space, we need to know that those designs are solid.
Yeah.
We need to be able to understand them and verify them.
You got it. And that's why there's a lot of research focused on developing what's called explainable AI.
Explainable AI. So Like AI that can show its work. Tell us how it got to its conclusions.
Basically, yeah. It's all about transparency and trust.
Makes sense. We need to be able to trust the technology if we're going to rely on it for something as important as space travel.
So it's a balancing act then. Embracing the power of AI, but making sure we understand it, that we can verify its work.
Exactly. It's about finding that sweet spot, you know? And I think we're getting there.
Okay, good to know. Now, I want to switch gears a bit and go back to something you mentioned earlier, the potential for aerospike engines here on Earth. You said something about hypersonic flight.
Yeah, that's one of the most exciting possibilities. Imagine being able to travel from New York to London in just a couple of hours. That's the kind of speed we're talking about.
Yeah.
Wow. That would be incredible. But wouldn't hypersonic flight be unbelievably hot? Like, how would the engine even survive those temperatures?
Well, remember that AI-designed Aerospike engine we talked about, the one that withstood exhaust temperatures of over 3,000 degrees Celsius?
Yeah.
That kind of heat resistance is going to be essential for hypersonic flight. We need engines that can handle those extreme conditions.
So the technology is already showing promise, even for applications that extreme.
It is. And besides speed, there are other potential benefits too. Aerospike engines are also more fuel efficient than traditional jet engines, and they don't create that loud sonic boom.
That's a big one.
Yeah.
So not only would hypersonic flights be faster, they could also be quieter and more environmentally friendly. That's a winning combination.
Right. It's still early days for hypersonic technology, but the potential is huge. It's not just about passenger travel either. We could also see hypersonic cargo transport, and even space tourism.
Wow, so this one technology could revolutionize so many different industries. But let's bring it back to space for a second. What are some of the specific missions where Aerospike engines could really make a difference?
One that comes to mind right away is missions to Mars. It's a long trip, right? And it takes a lot of fuel to get there. But with the efficiency of Aerospike engines, we could reduce the amount of fuel needed, which would make the whole mission more feasible.
Ah, so lighter spacecraft, shorter travel times, maybe even the possibility of sending humans to Mars and bringing them back safely.
Exactly. And it's not just about Mars either. These engines could open up the outer solar system too, places like Jupiter and Saturn.
It's mind-boggling to think about. But what about closer to home? Any potential uses for Aerospike engines in Earth orbit?
Definitely. Think about things like space stations or even those giant space-based solar power systems that people are talking about. Aerospike engines would be perfect for those kinds of missions, because they're so efficient and maneuverable.
It's fascinating to think about all the different ways this technology could be used. It really seems like Aerospike engines could play a key role in a whole range of space exploration projects, from small satellites to massive space stations.
I agree, it's exciting stuff, but like with anything new, there will be challenges along the way.
Oh, for sure. What are some of the biggest hurdles we're likely to face?
Well, one of the big ones is just the sheer cost and complexity of developing these engines. They require these advanced materials, and the manufacturing has to be super precise, and then there's all the testing to make sure they're safe and reliable. It's a big undertaking.
Right, and it's not just about the engines themselves. We also need to figure out how to integrate them into spacecraft and launch vehicles, how to make them work seamlessly with all the other systems.
Yeah, and then there's the whole issue of scaling up production. If we want Aerospike engines to become the standard, we need to be able to manufacture them efficiently and at a reasonable cost.
So it's a multifaceted challenge involving engineering, economics, manufacturing. It's a big puzzle.
It is, but you know what? Despite all those challenges, the potential benefits are just so huge that people are going to keep pushing forward. And I think eventually we'll see Aerospike engines become as common as jet engines are today.
That would be incredible. Imagine a world where we're hopping on hypersonic flights powered by Aerospike engines or sending missions to Mars as easily as we send satellites into orbit today.
I know, right? It's mind-blowing to think about.
It is. But let's not get ahead of ourselves. We're still in the early stages of this technological revolution. But it's clear that AI is going to play a major role in shaping the future of Aerospike engines, and maybe even the future of aerospace itself.
Oh, without a doubt. AI is going to be key.
So what are your thoughts on the future of AI in aerospace engineering? Where do you see this going in the next decade or two?
Well, I think AI is going to touch every aspect of aerospace, from the initial design phases to the actual manufacturing, mission planning, even piloting.
Wait, so you're saying AI could actually control entire spacecraft, like make decisions in real time during missions?
Absolutely. And not just that. AI could optimize flight paths, analyze sensor data, even diagnose and fix problems autonomously.
So we're talking about a future where AI is not just assisting engineers, but actually taking on more and more of the complex tasks involved in space exploration.
Exactly. It's a huge shift, but I think it's inevitable.
It sounds both exciting and a little bit scary at the same time. Like we're handing over a lot of control to machines.
I get that. And that's why it's so important that we develop AI responsibly, with ethics in mind. We need to make sure that human oversight is always there, that we're not just letting the machines run wild.
That's a crucial point. It's a reminder that technology is a tool, and like any tool, it can be used for good or for bad. It's up to us to make sure that AI is used to enhance our capabilities, not to replace or undermine human judgment and decision-making.
I couldn't agree more. We need to be smart about how we integrate AI into these critical systems.
Well said. Now, I think it's time to take a closer look at the heart of Aerospike technology, the thing that makes these engines so unique and efficient.
You talk about the virtual nozzle.
That's the one. It's a concept we've touched on a few times, but I think it's worth exploring in more detail. How does this invisible nozzle actually work? And why is it so crucial to the performance of an Aerospike engine? That's what we'll be diving into after the break, so stick with us because we're about to get really technical. Okay, so we're back and ready to tackle this whole virtual nozzle thing. It sounds pretty complex, but I'm sure you can break it down for us.
I'll do my best. It's funny. I like to think of a traditional bell-shaped nozzle. Like, imagine you're trying to force a river to flow through a narrow channel.
Okay, I can picture that.
So if the river's flow is just right, it'll work fine. But if the flow changes, you start to lose efficiency. Like if the river gets wider or narrower, that fixed channel just won't cut it anymore. And that's kind of what happens with the bell nozzle as the rocket goes up. The air pressure changes, but that nozzle, it can't adapt.
So it's like the engine is stuck in one mode, even though the environment around it is changing.
Exactly. But now imagine, instead of that fixed channel, you've got a flexible barrier, something that can expand and contract to match the river's flow no matter what.
Okay, that makes sense.
Well, that's basically what the virtual nozzle does. As the rocket goes higher and the air pressure drops, the virtual nozzle expands, giving those exhaust gases more room to flow.
So it's like the engine is breathing,
Mhm.
adjusting to the thinner air. That's pretty cool. But how does this virtual nozzle actually form? What's creating that invisible shape?
It's all about the interaction between the hot exhaust and the air pressure around it. As that exhaust flows around the Aerospike spike, it creates this kind of bubble. And the air pressure, it pushes against that bubble, shaping it into that virtual nozzle.
So the air itself is helping to shape the exhaust for maximum thrust.
Mm.
It's like a self-forming nozzle. That's a pretty wild concept.
It is. It's a great example of like designing a system that actually works with the environment, instead of fighting against it.
Definitely. But I imagine it's pretty tricky to actually design an engine that relies on this invisible, constantly changing nozzle.
Oh, absolutely. Trying to predict how that virtual nozzle will behave, it requires some serious computer modeling and a deep understanding of fluid dynamics. It's not easy stuff.
And then you've got to actually build the engine, make sure it can handle the incredible heat and pressure of a rocket launch,
Yeah.
and still maintain the precise shape needed to create that virtual nozzle.
Right. There's very little room for error.
So what happens if that virtual nozzle doesn't form correctly? Or if it becomes unstable during flight?
Well, that's why testing is so crucial. Engineers run all sorts of simulations and test firings to make sure that the engine performs as expected under all kinds of conditions. And they're always trying out new materials, tweaking the designs, constantly working to improve the engine's reliability and performance.
It sounds like a never-ending process of refinement.
It is. But that's what makes it so exciting. We're pushing the boundaries of what's possible, and we're learning so much along the way.
Well, I have to say, I'm pretty impressed with the potential of Aerospike technology. It seems like it really could revolutionize space travel and even high-speed flight here on Earth. It's a bit mind-boggling to think about.
It is. And this is really just the beginning. As technology keeps advancing, who knows what incredible things we'll be able to achieve with Aerospike engines in the future.
It's a future I'm definitely excited to be a part of. Well, I think that about wraps up our deep dive into Aerospike engines. We've covered a lot of ground today, from the basic principles to the potential applications, the challenges, and the incredible breakthroughs. It's been quite a journey.
It has. And for our listeners, if you're interested in learning more about this amazing technology, I encourage you to do some research, dig a little deeper, and see where your curiosity takes you. The future of space exploration is full of possibilities, and it's a future that we can all be a part of.
Absolutely. And don't forget to subscribe to Le Podcast de Philippe on YouTube for more deep dives into the world of science and technology. Until next time, keep looking up and keep exploring.